Can we consign the edge effect to history? The edge effect is a major concern in multi-well plate bioassays, and in this talk we're going to consider some approaches to handling it and other background plate patterns that sometimes are seen. So here is a 96 well assay plate, and the colours show the pattern of response that you see when all the wells have been treated in the same way. So this is what's called a heat map. And you can see that the edges are quite different from the rest, and this is a pattern that's very often seen. And notice that on a 96 well plate, the edges are 36 of the 96 wells, so that's a rather high percentage of the wells on the plate. This kind of background pattern and response can cause problems for the reportable value in two different ways. First of all, it can cause a bias in the reportable value. The other effect is on the precision of the estimate of the reportable value. The background variability, that is the variability across the plate, adds to the sample variability and makes your reportable value much less precise. If we Google the expression edge effects 96 well plate, we get a vast number of results. And most of the solutions that are proposed are technical kind of solutions, such as advanced plate designs that various people produce, or they're discussions around different techniques that can be used in the lab to minimize the impact of external conditions. But there aren't any, as far as I can tell, any statistical approaches proposed by anybody. And this is the focus of this talk. Considering other sectors in the life sciences area, we find that in agriculture there are many examples of sort of similar types of problems. So in a field, for example, you can have a dry area on one side and a damp area on another, or shadow or wind, and all of these things cause effects across the field which are kind of similar to what you might see on a plate. This photo is of R.A. Fisher, who is a very famous statistician who wrote a book back in the 1920s called The Design of Experiments. Fisher had the F test named after him, you may have heard of that. And one of the designs for experiments, which was for use in agriculture, is called the Latin square design, and I'm going to talk about that in the next couple of slides. In a Latin square design, the field, or the plate in our case, is divided up into an equal number of rows and columns. So in this example I've shown we have 8 rows, A to H, and 8 columns, 1 to 8. And the design of the experiment is such that each of your treatments appears in each row and in each column. So that implies that there are 8 treatments in a Latin square design. So we have 8 treatments, 8 rows and 8 columns in this example, although that number can be any number you like. Here we show the first treatment, A, and how that could be allocated in this design. So you can see this treatment A appears once in row A, once in row B, once in row C, etc. And it also appears once in column 1 and once in each of the other columns. Here we've added the next treatment, treatment B, and treatment B, like A, appears once in each row and once in each column. Here we've added treatment C, again similarly appears once in each row and once in each column. And here we finally have the full Latin square design with treatments A through H arranged so that each one appears once in each row and once in each column. And this, as you can see, there's a beautifully balanced design where there's no bias in the comparisons between the treatments, which is what we're interested in, caused by any variation across the plate or down the plate. So how can Latin squares be applied to bioassay? Is this a possibility? Well, one of the guidances, which is microbiological assay of antibiotics, actually mentions the Latin square as a possibility. I'm going to show you an example of an antibiotic assay which is run following that guidance that we just referred to. These are mock-up data, but we have seen results extremely similar to this in real life. So the reference sample and the test sample are tested at 4 doses each, and that gives us 8 total treatments. So the Latin square will have 8 rows and 8 columns, and each one of those treatments appears once in each row and once in each column. So there are 4 doses. We've slightly offset the reference and the test to show them more clearly apart. So we have 8 treatments, a pair at each dose, and we've just coloured the rows here to show that there is really a row effect. So the black dots and squares are row 1, the red are row 2, etc., all the way down to grey in row 8. At each dose level, that is test on the left and reference on the right, the black is at the top, or very near the top in each case, which is row 1. The red is close to the top, the next down in row, which is row 2, and all the way down to the grey, which is row 8, which is either in fact it's actually at the bottom in every case. So you can see that as we go across, or rather down this plate from row 1 through to row 8, we are getting reducing responses. So there is a clear row effect in this particular example. So here we've illustrated the data in a slightly different way. We've ignored the rows and just simply coloured the reference in blue and the test in orange and fitted independent straight lines to those 2 samples. And here you can see that if you ignore the rows, this just simply looks like a relatively noisy assay. The dose response model is quite nice and linear, and they do look quite nice and parallel as well. Here we've fitted the linear models to each of the rows separately, and you can see that these are quite tight, that we've got both the row, the reference and the test samples at the top in blue, and they're quite close together and quite nice and parallel. The next one down is the green ones, which are kind of hidden in this green-yellow area here, and again they're quite tight, quite parallel and quite close together, through orange, through red, through black and grey, right through to the purple at the bottom. So what we've actually got is a series of 8 pairs of test and reference models. This next slide shows just row 1 and row 8 to clarify what's going on. And you can see here it looks like 2 repeats of the same assay. So it's clear that what we've really got is 8 repeats of something that's quite similar and quite tight. And in fact, all these points are rather close to the line rather than having a lot of noise around them, as we saw in the very first slide. So the Latin square is a design which removes the bias in the estimate. As we said at the beginning, it's a nice balanced design, and where there are row and column effects, these are balanced out because every treatment appears in every row and in every column. However, what it also does is allows a statistical analysis which can adjust for the row and column effects. So that removes those row and column effects from the estimate of the relative potency to give us a more precise estimate. So the plot here shows 3 different approaches from the same data set. The first estimate on the left is the estimate of relative potency, which you can see is about 92.5%. But this estimate just ignores the rows and columns. It's like an estimate from the first slide we looked at, which is just a rather noisy assay, where the 95% confidence interval ranges from below 85% to above 100%. The second estimate in the middle of the plot shows the relative potency estimate where we've deleted the top and bottom rows because we've seen that there's a row effect. So we've deleted the top row, we've deleted the bottom row, and just done a simple analysis. And what that's done is given a pretty similar estimate and a slightly tighter confidence interval. And that is because there is a strong row effect which is contributing to the noise in the data. The third estimate to the right of the plot shows the estimate using all the data but adjusting out for the row and column effect. So it's like saying, let's estimate the relative potency for each row separately and actually each column separately, which I'm not going to go into because it becomes quite complicated. Essentially, we're estimating the relative potency separately for each row and then combining all of those estimates, assuming that actually what's being estimated is the same quantity for each row. And this again gives us another estimate of the relative potency, which is very similar across the plot. You can see it's in a similar position at about 92.5%. But the key point is that the confidence interval is much narrower, and that's because we've managed to remove the noise created by the rows and columns. So just to recap on the benefits of the Latin squared, it first of all removes the bias introduced by row and column effects, and also the statistical analysis allows us to come up with a much more precise estimate of the relative potency from the same data set. This slide shows a stained glass window in the college chapel of Fisher's College in Cambridge University in honour of his invention of the Latin square design. And you can see it's a 7x7 Latin square, and each row and each column shows each colour once. So the purple colour appears once in each row and once in each column, etc. So Fisher was very famous for his Latin square design. The question really is, the Latin square works well in field experiments. It does need quite a lot of control, but it does work well in a field. But is it applicable in a 96-well plate assay? Well, if we think about it, usually there would be too many treatments to apply in a Latin square design. So for example, if we've got a 4-parameter logistic model with 8 doses for each treatment, even if we only have one test sample, we'd have a reference standard and a test giving us at least 16 treatments. So that means that a Latin square, a full Latin square, would have to have 16 times 16 wells in it, which is a large plate. And also it's very complex to implement without a robot because it takes very careful manipulation of the doses. So can we try and use this concept of retrieving and correcting for the information in the rows and columns, for example, without doing a full Latin square design? The aim would be to avoid wasting wells and or resources. So can we come up with a balanced design which would remove any bias and couple that with a statistical analysis which allows us to get the most precise answer possible from the data that we have? So we addressed this question via a simulation study, and the assay design we picked to study consisted of a test sample and a reference standard. Each of those had 12 doses, and we gave them 4 replicates each, totaling 96 wells. And we assumed that the dose-response relationship was 4-parameter logistic. This plot shows the situation that we simulated. So we've got 12 doses, a 4-parameter logistic model for each of the reference and the test samples. And what we simulated was the situation where the relative potency of the test with respect to the reference was 61%, and we had a within group variability which was 0.1, and you can see here that the lower asymptote was 0 and the upper asymptote was 2 in response. So this is the situation we were simulating, and we examined a series of 3 potential patterns of background effect on the plate. The first one shown here, we labelled exponential. That was because we set it up to be high on the edges and very rapidly dropping off towards the middle. This is the kind of a heat map that you would see for this plate if you ran it with blanks. The effect on the outside is very high and then it drops off very steeply towards the middle. The second background pattern we simulated was less steeply dropping off towards the middle. So you have effects at the corners which kind of reduce towards the middle of the edges and reduce towards the middle of the plate as shown, and we called this a smooth background. So it's a similar pattern to the exponential one but with much less steep sides, if you like, to the effect. And this third background that we simulated we called the diagonal background, and this is where you have an effect going diagonally from top left to bottom right corner across the plate. And this is something that we have clients reporting to us sometimes. So far we have a dose response model for the reference standard, we have a dose response model for the test sample, and we have 3 different potential background effects on the plate. So the last thing to consider is the design of the plate for the assay. And we've looked at 3 different designs for the plate. The first one is shown here. It's a simple design where the reference is shown in black, the test material is shown in red, and each is repeated 4 times. There are 4 replicates for each, and they simply go from left to right in terms of the doses. So the first dose, lowest dose, is at the left, and the top dose is at the right. So doses increasing from left to right in each case. And you'll notice here that there is a slight bias towards the top for the reference, and there's also biased from left to right because the low doses are always at the left and the high doses are always at the right. This means that so long as the background is completely uniform across the plate, there won't be a problem. But with any other background effects, there may well be bias or precision compromised by using this design. This slide shows the second design that we've simulated, so we've called it the structured 1 design, and this aims to remove the bias from top to bottom and from left to right in the plate. So it takes reference and test alternately, but on the left hand side it starts with the reference, on the right hand side it starts with the test, which removes that bias from top to bottom across the plate. And then what we've also done is to reverse, in the bottom half, reverse the order of the doses. The third assay plate layout we've simulated we call the structured 2 design, and this takes reference and test alternately, doses increasing from left to right, followed by the test doing the same thing. In the next 2 rows we've got the reference and test but with the order of doses reversed, and then that pattern is repeated in the last 4 rows. So this design removes the bias from left to right across the plate, but it still retains the slight bias towards the top for the reference. The reference is slightly closer to the top and the test is slightly closer to the bottom. So there's still a bit of a bias in there. However, this design would be easier to implement because it's a bit less complicated than the second one. So the simulations proceeded as follows. We took each background pattern in turn, and we also did the same thing for a uniform plate. So for each background pattern, took each plate layout in turn, and for each of those we simulated 1,000 assays, and that involved identifying for each of the 96 wells on the plate which treatment they would be given for the particular plate layout. So that would be either it would be the reference or the test sample, and we would find which dose was being given to that well. And for those we would simulate the 4-parameter logistic response, and then we would add the background for the particular background pattern in question. So we have 3 background patterns plus uniform, that's 4 different patterns for the background on the plate. We have 3 plate layouts, so we've actually got 12 different scenarios, 4 backgrounds and 3 different plate layouts. And for each of those we've simulated 1,000 assays, so 12,000 simulated assays. For each of those assays that we've simulated, so in each case we've got a data set of 96 points which now needs statistical analysis. And we conducted the statistical analysis in a few different ways just to see the effects of doing different things with those data. So for the simple plate layout, which is the very first one that we looked at, we analysed the data in 2 different ways. Firstly, we just ignored the background and just analysed it in a simple, straightforward 4-parameter logistic model, ignoring whatever's going on in the background in rows and columns. And secondly, we did what a lot of people do when they think there's an edge effect, which is simply to exclude all of the edges. So we excluded the 36 wells that are around the edge of the plate. For the structured 1 layout, which is a slightly more complex plate layout, we simply ran an analysis which allowed us to adjust for the row and column effects. That analysis was not possible for the simple plate layout because the rows and columns were completely mixed up, confounded, we say, with the treatments, with the reference and test treatments. So it wasn't possible statistically to adjust for the rows and columns with the simple plate layout, so we couldn't do that. But we could do that for the structured 1 plate layout. We could also do that for the structured 2 plate layout. So what we're really aiming to do here is to do the best we can statistically with the data, and the best we can statistically is to adjust for rows and columns where that's possible, but where it isn't possible, to try an alternative approach to adjusting for the edge effects. So here we start to show the results from the simulations, and I'll show these one at a time for the different background patterns that we assumed. So the first one's the simplest one, which is uniform. This little diagram here illustrates the background that's going on the plate. And the x-axis on the plot is the estimate for the relative potency, and the y-axis for the plot is essentially represents the precision of that estimate, which is illustrated by the confidence interval width for the log relative potency. So the smaller that width is, the better, and the closer to the true relative potency we are, the better for the estimate of relative potency. And we know the true relative potency because we've actually simulated it, and it's 61%, or 60.7%, and that's shown on here. Now, each of the dots represents a particular simulated plate. We've simulated 3 situations here corresponding to the 3 different plate layouts. So remember, we've got a simple plate layout, and we've got a structured 1 plate layout and a structured 2 plate layout. For the simple plate, we've analysed the data in 2 different ways, once with all the data and the second time excluding the edges. So let's look at that first of all. So the easiest cloud of points to see here is the blue cloud. And the blue represents the analysis of the simple design with the edges excluded. All of the other ones are kind of lying on top of one another. So you can see the yellow, which is the structured 2 design, the green, which is the structured 1 design, is kind of underneath the yellow, and the black, which is the simple plate design, is also underneath that. So the only difference really here with a uniform background is between the simple design with the edges excluded, that's the blue cloud, and all of the others. And what that's telling us really is that because there's no background, it doesn't matter what your design looks like because there is no bias anyway. So the fancy designs don't really help us here. And similarly, because there is no background effect, there is no need to exclude the edges. So the only difference here is that excluding the edges shifts that cloud of points upwards. Although we get an unbiased estimate, which is lying on the true relative potency, the variability on average is much higher. And that's, of course, because we have lost 37.5% of our data. So we've got less information, so less precision for our estimate on average. This next slide shows the results when we have the exponential background. That is, we've got a big effect around the outside, which drops off quite quickly towards the middle. And again, we've got 4 clouds of points here, and you can see these much more clearly now. And again, basically we've got 1,000 dots in each case. If we look at the blue ones and the black ones first, those represent the simple plate layout, analysed in the black with all the data, and in the blue excluding the edges. So you can see in this case, just comparing those two, that the black ones are slightly biased. That big black dot is lying slightly to the right of the true relative potency. And also the cloud of points is much higher up the y-axis than the blue, which is telling us, and the blue big dot actually is also lying quite close to the true relative potency. So that tells us that in this situation, where we've got a strong effect on the outside but much less in the middle, that actually getting rid of the edges does virtually correct for the problem with the background. It brings us back to the lack of bias, and also it gives us a much reduced variability. So that's quite a good thing to do in this situation. However, if we went for one of the structured designs, we can do even better. So with the structured 1 design, which was the relatively fancy one, we've got the green dots, the middle of which is lying again right on the true relative potency, so we have managed to get rid of any bias, and we've got an even lower cloud here, so showing that we've got a more precise result than we got with the blue dots, that is with the simple design excluding the edges. In this situation, the structured 2 design didn't really help very much. It has seemed to have got rid of this particular bias. The yellow dot is on the true relative potency, but we've still got quite a lot of variability. This slide shows the results where we have the smooth background on the plate. And here, if we first of all compare the blue and the black clouds of points, you can see that that represents the simple design with and without the edges. And here, excluding the edges actually doesn't really help you very much at all, because that's only a very small part of the problem on the plate. In both cases, we've got what looks like quite a substantial bias. The dot is to the right of the true relative potency. and the cloud of points is relatively high, indicating that they're both quite variable. The blue relatively on average more variable because we've thrown out data. Comparing the results for the two structure designs, again we see that the green dots are unbiased and relatively less variable than the yellow ones. The yellow ones again are unbiased, but they're more variable than the green ones. And this slide shows the results for the diagonal background, and this really does separate out the different methods. At the top right is the plot showing the background. Again, if we first of all compare the simple without edges and the simple with edges, the simple with edges, the black cloud, is really quite biased, and that's not really very surprising given this kind of background. In this particular situation, and I think this is really a chance lucky situation really with this particular background, the simple design excluding the edges does seem to have got rid of most of the bias, but it's still quite a variable result. The structured one design is unbiased and is nice and low down on the variability stakes. The yellow structured design has really not helped all that much at all. It's still pretty biased and it's still pretty variable. So to summarise, the results are arranged by background pattern across the table here. So just to recall, for the uniform plate background, the simple plate layout works absolutely fine with that. So that's obviously the best thing to go for because it's simplest to implement. And it's best to include all the wells in the analysis, and there's no need to do anything fancy with the analysis. So that was the simple best way to do it in that case. That's what you'd expect. Where we have the exponential plate background, two different approaches work virtually equally well. The simple plate layout works reasonably well. The analysis is much better if you exclude the edges. We got very similar results using the structured one design, which is a bit harder to implement obviously, including all the wells in the analysis and analysing, adjusting for the row and column effects. So those two approaches gave us very similar answers. For the smooth background, there was a clear benefit of using the structured one approach, all the wells in the analysis and adjusting for row and column effects, and the same thing was seen for the diagonal background. So to conclude, we have some recommendations. The first thing we would propose is that before you decide how to design your assay, you assess the background on the plate using a heat map, which I think lots of people do anyway. And if you discover that the heat map isn't uniform, it's showing some kind of pattern on the plate, then it is possible to structure the plate layout for the assay to minimise bias in the reportable value, so to try and balance the reference sample and the test sample across the plate according to the background. And secondly, to use statistical techniques to make that adjustment for the row and column effects in order to handle the precision of the estimate. So just to summarise, we've shown that there are ways to avoid having to exclude the edge wells. So we can add back those 36 excluded wells. And when you compare that with the 60 that left if you do exclude them, you're actually increasing the plate capacity by 60%. So in practical terms, we think that's a really good thing to try and do, and we would like to suggest that you can consign the edge effect to history. Thank you very much.